continue our discussion on p-n junction under biased conditions. Biasing means that we apply a external voltage, and as we discussed, there are two possibilities for biasing. One is the forward bias, in which the positive terminal of battery is connected to the p type material and n type material is connected to the negative terminal. And we have seen that the field which is applied has a direction which is reverse of built-in field, and as a result the potential height of the barrier falls. The diffusion of majority charge carriers, electrons from n side to p side and holes from p side to n side constitutes what is known as forward current. Forward current increases exponentially as we increase the forward voltage, and the resistance of the device is extremely small, of the order of 10, 20, 30 ohms. Now, we will discuss about the reverse bias. The reverse bias circuit is this is p type, n type, this is the junction, these are the ohmic contacts, and then we apply reverse bias V. Now, look at this was the direction of the built-in field and this is now positive. So, this is the direction of the applied field. The two fields are in the same direction. As a result, the potential barrier height goes up and the diagram becomes this. This is p type, p side, this is n side, and this is the Fermi level of p side, and this is the Fermi level. Again they are separated, they were aligned together when there was no applied field. So, this separation is equal to the energy equal to the applied voltage V, and that is Q V. Now, as it is evident that the potential height has increased and the majority carriers, electrons here and holes here, have absolutely no chance to cross over to the other side, and so they are unable to diffuse. So, the first point we note that the majority charge carrier diffusion is not possible. No majority charge diffusion, and hence the current component does not come from majority charge carriers. However, look at what happens, because p side, the p semiconductor has electrons in minority and holes on the n side are in minority. These charges will drift under the applied field. Mind it, this is the positive side, this is the negative side, and hence these electrons will drift under the field, and as you will remember that this is also a downhill for holes. So, these minority holes from p side will drift under the applied field towards the p side. So, these are the charges which are minority charges, they constitute what is known as reverse current, actually reverse saturation current. I will discuss, I will tell you that why it is very small and why it is voltage independent, and on what factors does it depend. Now, so minority charge carriers, minority charges constitute reverse saturation current. Now, which minority charge carriers? The minority charge carriers, actually these are all thermally generated. Now, the charges far away from the junction, here the electron here, this region is p type which has majority of holes. So, it is very likely that the electrons in the p region, when they try to drift under the applied field, they will recombine. There is a high probability of recombination for the electrons in the p region, the electrons which are far away from the junction. And similarly, the holes which are actually almost uniformly throughout the material. So, the electrons in the n side which are far away from the junction, they will again recombine in the n region with the electrons, and they will not contribute to the reverse current. But within the diffusion, within the depletion region, or the electrons in the p side very close to the junction, they will be able to drift. Similarly, the holes which are very close to the junction on the n side, they will be able to drift towards the p side. Now, the direction of hole movement is the direction of current. The holes are moving this way. So, the direction of electric current is in this direction. This is reverse saturation current. So, this is clear that the direction of this current is opposite to the current which was flowing in the forward direction, in the forward bias case. So, this is called reverse saturation current. Reverse saturation current, and that comes from the minority charge carriers on the p side, the electrons, and holes on the n side, which are within the depletion region or around the junction. Now, this is, we have said it is reverse, and I explained that the direction of this current is reverse of the direction which of the current in the forward direction. Why it is saturation current? This is saturation current because the number of these minority charge carriers, that simply depends on the temperature. So, if we increase this reverse voltage further, then we are simply changing this height more, but that will not change the density of minority charge carriers or the number of charge carriers which are closer to the junction, and hence reverse saturation current is independent. It is almost independent of applied reverse voltage. Why I have written almost? That when you draw the actual characteristics, IV characteristics in the reverse bias, then there is a very small dependence on this voltage. This small dependence comes from the fact that there are defects on the surface of the device, and this gives rise to some movement of charges, and that constitutes that gives rise to this small voltage dependence on the reverse voltage. So, it should be now clear that what forms the reverse current, why it is called reverse, and why it is saturation current. So, this is, and these are the IB characteristics. Forward current was this, and this reverse current is a drift current. This is not diffusion, drift current, and this is in microamperes or nanoamperes, very small, while this is normally in milliamperes, this forward current. So, this is about this. Another very important point which we can derive from these reverse characteristics, that this, when we change the voltage significantly, there is a insignificant change in the current. That means that the reverse resistance is extremely high, while the forward resistance was just few tens of ohms. This is normally in kilo ohms and meg ohms. This is around meg ohms. So, very high resistance. The width of the depletion region, width of depletion region, it was said earlier that it is a function of the applied voltage, and this increases with the reverse bias voltage. As we increase the reverse voltage, the depletion width increases. The relation is this, and we have to substitute voltage with proper sign. When this is negative, then this is this sign becomes plus, and hence W, the depletion width, gets proportional to the applied voltage in the reverse bias. And physically you can understand that why it should increase, because the reverse bias pulls away the majority charge carriers further away from the junction, and hence more ions, those impurity ionized ions, they will be uncovered, and actually they form what is known as depletion region, and hence depletion width increases with the reverse bias. The IB characteristics, as we were discussing earlier, I have given you the expression I equal to I 0 exponential V eta B t minus 1. Here for reverse bias, this voltage V will be negative, and hence exponential term will be approaching 0 very quickly. So, this relation gives you I equal to minus I 0. This minus sign is the direction of the reverse current, which is opposite to the forward current, and if you go in the deeper physics of the device, then this reverse saturation current is given by Q. A is the area of cross section of the junction, and dH P N O L H plus dE N P 0 by L E, where Q is the charge A is the area of cross section, higher is the area of cross section, higher will be the reverse current, and dH is the hole diffusion constant, and P and O is the hole density on the n side, that is minority density, and LH is the diffusion length of holes, and these are the corresponding parameters for the electron. So, this is all about the IB characteristics of PN diode and the currents in the forward direction and the reverse direction, how the depletion width varies with the applied voltage. It will decrease with the forward bias and it increases with the reverse bias, and the resistance of the diode in the forward direction, always remember, is extremely small, just few tens of ohms, but in reverse bias very high impedance of the order of megohms is obtained. Now, there are several properties associated with the junction. Some of them we have talked, the contact potential and the depletion width and so on. The next is junction capacitance. Junction capacitance. Here this is the PN device. Now, you will recall that this depletion region is a high resistivity region. It is like a dielectric insulator, and the conductivity of P side and N side, this is relatively several order of magnitude higher than the resistivity of the depletion of the let us talk in terms of conductivity, that conductivity of these two regions is much higher than the depletion region. So, this is almost like a parallel plate capacitor. What happens in a capacitor? These are two conducting plates and separated by a dielectric. A dielectric is a high insulator. So, this is the insulator, this is equivalent to the two conducting sides, and hence PN junction must have a capacitance, and this capacitance is called transition capacitance, junction capacitance or transition capacitance. The simple parallel plate capacitor expression is A is the area of cross section of the junction, and this is the permittivity of this depletion region of the dielectric divided by the depletion width. This permittivity is equal to permittivity of free space into the real part, the dielectric constant, which is around 11.5 for silicon. Now, if we actually, even from a rigorous theory, as you can find in several books like Millman-Helkias integrated electronics, the rigorous theory also gives the relation for the transition capacitance, which is this. While we can see that simple analogy of this junction capacitance with the parallel plate capacitor also results in same. Here W is the depletion width, this is W, and if we substitute the expression of the depletion width, then it works out to be epsilon q a n a n d 2 n a plus n d to the power half and V b minus b minus 1 by 2. This is the expression for the capacitance, and this is the function of the applied voltage. Actually, there are specially designed PN diodes which are known as varactors, which make use of this property of the junction, that its transition capacitance depends on the applied voltage. When in reverse bias, when we take it with proper sign, and because this is minus 1 by 2, so capacitance you will find inversely proportional to almost 1 by V to the power half. It falls. So, that specially designed diodes are known as varactors. There is a capacitance in the forward direction also, that is known as diffusion capacitance. Diffusion capacitance. We now understand that when the diode is forward biased, lot of majority charge carriers, that is holes from the p side, are injected to the n side, and from the n region the electrons are injected into p side. So, depletion width falls and have large currents flow, but there is a capacitance which is known as diffusion capacitance, because depletion width is very small in the forward bias case. So, diffusion capacitance is actually very large. This is in the reverse bias, the capacitance per unit area is of the order of 100 or 200 picofarads. In the forward bias, this diffusion capacitance, though it is high, but actually because of the heavy currents, all effects are actually dominated by the current. So, the diffusion capacitance does not play that important role as the junction capacitance or transition capacitance. So, this is about the junction capacitances. Now, we take another aspect of the IV characteristics and of the device. This is junction breakdown. Junction breakdown. If we take a PN diode and this is I, this is V, and forward biased gives exponential rise in current. To limit the current, a resistance is used which is known as current limiting resistor. That will save the diode from burning because of heavy currents. And in reverse bias, as I said, the currents are extremely small. These are in microamperes and many times nanoamperes. But if we go on increasing the reverse bias, a situation comes that the current starts rising. This is because of the new phenomenon, and that is known as breakdown, junction breakdown, junction breakdown. When we apply the field to a diode, because they have relatively much lower resistivities as compared to the depletion region. So, almost all the field appears along the depletion region, and this field, as we increase the voltage, say 10 volts, 5 volts, and if we divide by the width, which is of the order of 1 or 2 or 3 micrometers, then the field becomes kilovolts per centimeter, which is very high field, and that gives rise to what is called junction breakdown. I repeat, if we go on increasing the reverse bias across the junction, then normally we will observe very small current, very feeble current in microamperes or nanoamperes, which is 3 or 4 magnitudes lower than the forward current. But if we keep on increasing the voltage, after a certain voltage the current starts rising, and this happens due to another phenomenon which occurs, and that is junction breakdown. Now, there are two processes of junction breakdown. One is avalanche breakdown, and the other is Zener breakdown. What are these two processes? Let us first talk of avalanche breakdown. In the reverse bias, mind it, breakdown occurs in the reverse bias, and if we go on increasing the applied voltage, then field in the depletion region increases. As a result, the thermally generated charge carriers in the depletion region and around that, they get very high energy, they drive very high energy from the applied field, and sometimes this energy becomes so high that these charge carriers may make a impact on the bound electrons of the crystal, and they will knock out those electrons. For example, we can depict like this, that this is silicon atom and these are the bound electrons. These are all silicon, these are the outermost electrons which are the valence electrons, and this is the highly energetic electron. This gains enough energy that it makes impact here, and it is able to knock out this electron, so that they become 2. Now, I mean they get multiplied, and in the applied field is very high. This continues, and quickly means in a microsecond, for example, they will be multiplied and the current will start increasing, rising as we go on increasing the reverse voltage. Now, this phenomena of breakdown has been utilized for a very good purpose, and we will see that. Normally, for a PN diode, this breakdown is very gradual, but by proper doping, proper design of the PN junction, we can make it that the breakdown occurs very sharply. So, here this is V, this is I, this is that reverse saturation current, and then breakdown occurs at a well defined voltage which is known as Zener breakdown voltage. Now, these are the characteristics, I V characteristics of a what we call Zener diode. This was the avalanche process which occurs when the thermally generated charge carriers acquire very high energies from the field and they knock down the electrons. In the Zener process, Zener breakdown, in the Zener breakdown, the field, there is no impact, there is no collision, but the field is so high in the depletion region that electrons are ruptured, they are pulled by the field itself, by the influence of the field. The electrons are pulled out of the crystal, and this way they are multiplied. So, this process is known as Zener breakdown. Now, if you look at the expression for the depletion width, then we will see that when the two regions are highly doped, p side and n side, then depletion width is low, and that means the same voltage will give much higher fields and in the depletion region. So, the Zener breakdown occurs in the diodes which are having high level of doping on the p side and n side, while avalanche breakdown occurs when the two sides of the diode are just not too heavily doped. But very important thing, whether the process is avalanche breakdown or the process is Zener breakdown, the diode is always called Zener diode. Zener diode, and remember that Zener diode will have a well defined breakdown voltage, which is known as I said, Zener voltage, breakdown voltage, Zener voltage. Now, the circuit symbol of the diode, simple diode, the circuit symbol is this. This is for ordinary diode, and for Zener diode this is circuit symbol. So, remember this little difference here, that gives you, that tells you whether in the circuit design whether this is a Zener diode or a simple diode. This is the higher voltage side. When this is connected to P battery side, then the ordinary diode is forward biased. In the remember that Zener diode is always operated in the reverse bias case, and the voltage has to be higher than the breakdown voltage. That means, in this region, beyond this breakdown region, it is operated. Now, there are some interesting and useful properties of a Zener diode. From this knee, this is the current, and voltage remains constant, equal to the breakdown voltage. So, this is, if we call, let us consider a small circuit. This is a resistance R, this is the applied battery, and here is this current I z. Now, this is a useful property of the Zener diode, that through this different amounts of current may flow, but the voltage drop across this will remain same, and this will be equal to V z, the breakdown voltage. And how much voltage we can apply if we change the voltage? if this voltage changes from V1 to V2, both are higher than the breakdown voltage, then the drop, because the current will change from here to, for example, the maximum current here, which is I Z M. So much current will vary, and hence the drop, the extra drop, the difference of the two will be across this resistance, but this voltage across the Zener diode remains constant, and this is very important and significant. And what is the maximum power, maximum current that will be governed by this expression P max, the maximum power for which a Zener can be subjected is I Z M, that is the maximum current which will flow through the Zener diode, and this is of course the voltage is fixed. So, this should not be violated. And what is the value of the maximum power which can be applied across which the diode will withstand is given by the manufacturer in the data. So, this is about the Zener diode, always operated in the reverse bias, and if we change the input voltage, but this voltage, but the voltage across the diode is that does not change, remains fixed and equal to the breakdown voltage. There are different series, different types of Zener diodes which are available, ranging in the breakdown voltage from say 5 volts to almost few hundred volts. There is a very large range of these voltages, and one of the biggest use application of the Zener diode is as a voltage regulator. That is in or reference, as a reference voltage. There are many situations in electronics where we require a reference voltage, so that other voltages may be compared with the reference voltage, and invariably Zener diode of appropriate breakdown voltage, that will be the reference voltage, and we can use this device conveniently. Regulation becomes, as I explained, that if we change the voltage from V1 to V2, the currents will change passing through the diode, but the voltage will always remain equal to the breakdown voltage, and the extra voltage, the potential will appear across the this resistance, because R is a function of this. Various quantities of R will flow, and larger of various currents will flow, and higher is the value of current, larger will be the voltage drop here, but here the voltage drop remains fixed, which is equal to V Z. This was about the device and its physics, the properties associated with the diode, and now we talk of diode in circuits. Diode in circuits. We have talked about IV characteristics, and they were in forward bias, they were like this. This is exponentially varying current. but when we talk of circuits, then we have to approximate these characteristics. And so, the simplest approximation is to treat the diode as having ideal characteristics. Now, we are talking of simple p-n junction. The Zener thing we have finished, that is a special diode used for regulating and as a reference voltage device. This is the simple p-n junction, and we will talk about its circuit applications. And before that, we have to talk about the electrical behavior which is described by the IB characteristics. Actual one is this in the forward bias, but this makes analysis very complicated. So, we have to go for certain approximations, and that we will see here. So, one is ideal diode characteristics. Here this drop of voltage across the device is assumed 0. So, the for ideal behavior the characteristics are these are the characteristics. That means, the forward resistance is taken 0, and the reverse, that means in the reverse biased case, the reverse resistance is taken as infinite, and no current flows. In the forward direction, the resistance is taken as 0, and in the reverse direction, this is a very feeble current, but we assume, because these are idealized characteristics. So, we assume that this current is 0, and obviously, the resistance of the device, the impedance, that will be infinite. So, these are many times the diode is treated as an ideal diode, and we use these characteristics and we remember these things. So, that means when the diode is forward biased, it is almost it is a switch. This is one state, the circuit is short circuited, here 0 current, infinite resistance. So, the diode is in the off state, here it is in the on state. So, this is the diode acts as a switch. The ideal switch, where forward resistance 0 and reverse current 0. Now, these are the highly idealized characteristics. Practical characteristics are practical diode characteristics. These are like this, and this is for silicon diode, this is taken as 0.7 volts. Diode drop in the forward direction, that means here, this is the forward bias diode, and when this voltage is above 0.7 or close to 0.7, then drop across this, that is the meaning. When the diode is in on state, practically we take, if it is silicon diode, 0.7 volts drops, that means 700 millivolts for silicon diode, and this is around 300 millivolts for germanium diode. So, these are the practical diode characteristics, they remain the same. That means, in the reverse bias the current is 0. This is most widely used for any precise analysis of any diode circuit. These are the characteristics which are used. Of course, for many applications even idealized characteristics are good enough. Now, there is third characteristics which are called piecewise linear characteristics. Piecewise linear characteristics, and these are this, where the slope, because there is a large variety of diodes having different characteristics. So, the forward resistance is also different for different type of diodes, and so the slope of this slope is equal to 1 by R f, where R f is the forward resistance. Forward resistance of the diode, and this is very low, as it was said in the beginning. So, R f is of the order of, this varies from diode to diode from 20 to 50 ohms. So, these are the three kinds of IV characteristics which we make use in circuit analysis. And then before going for few other applications of the diode, let us see that what we have said so far. When we bias the diode in the forward direction, the current increases exponentially, and the current should not exceed the maximum current, maximum rating as we call it, as prescribed by the manufacturer. For each number of the diode, we put a series resistance with the diode, which is known as current limiting resistor, and that will prevent the diode from damage. And when we reverse bias it, then actually this the resistance of the device is very high. A reverse bias PN junction will have very high resistance, very high impedance, and which is of the tune of few megohms, and there are, depending on the fact that how much precision we require in our analysis, I have given 3 different sets of characteristics, and the ideal characteristics, these were the real IV characteristics, and these are the idealized diode, and so the forward current was taken as very high and the forward resistance was taken as 0, while the reverse resistance was taken as infinity. And in the practical diode characteristics, these are the practical diode. In forward bias, we take this exponential rise as a straight line and the voltage drop for silicon diode as 700 millivolts or 0.7 volts, and for germanium around 300 volts. There are third characteristics which are called piecewise linear characteristics. For very precise value of for precisely analyzing any circuit, we have to adopt for this third type of characteristics, and here the slope will vary from diode to diode. So, this resistance of this is we can find out from the slope. If we have the characteristics, we can draw a tangent at the operating point, and from that slope we can find the forward resistance. If we drop this tangent at different points of these characteristics, slope will vary and hence the forward resistance will vary, and this will be high in this region here if we draw a tangent, then if we draw a tangent here. So, actually the tangent is to be drawn at the operating point. What is the range of voltages on for which we are operating the diode. So, actually these characteristics prove useful in that case. So, the slope is equal to 1 by Rf. We will continue now with the diode applications in circuits. These diode applications, different kind of circuits are there which make use of these diode properties, and we will be discussing them one by one. So, some of the applications which we will cover, these are diode as a rectifier, diode in clipping circuits, which are known as clippers, and clampers. Clamping circuits or simply clampers. And these we will be studying one by one, and then we will start the next unit, which will be on transistor, and our knowledge will, this diode knowledge will be very useful in that case also.